Now I am going to start module 2 of chapter 10. This module is devoted to the discussion on two important phenomena, namely the phenomena of dispersion and dissipation. Now I am going to tell few words about the phenomena of dispersion. Suppose we have a one-dimensional wave equation. The equation is given by del 2u del t square equals to c naught square del 2u del x square, where c naught is a constant. Now, we want the solution of this equation in travelling waves form. So, the solution can be written as u is equal to f of kx minus omega t, where k is the wave number and omega is the frequency of the wave. Now, if we substitute this solution to the equation, we obtain that the phase velocity of the wave, which is defined as small c, is equal to omega by k equals to c naught for this case. That means, for a linear wave equation, c equals to c naught, which is a constant. These type of waves are called non-dispersive waves. So, for non-dispersive wave, phase velocity c is constant. For dispersive wave, c is equal to some function of wave number k. Now, what is the difference between a dispersive wave and a non-dispersive wave? Suppose there is a non-sinusoidal disturbance, and we know that this type of disturbance can be written as combination of sinusoidal waves. Now, for non-dispersive wave, since the velocity of all waves having different wave numbers are same, for this case the shape of the disturbance will remain same with time. On the other hand, in case of non-dispersive wave, the shape of the non-sinusoidal disturbance will not remain same with time. And this particular phenomena is known as the phenomena of dispersion. In this section, I am going to discuss about this phenomena taking simple wave equation. First, we take one-dimensional wave equation, which is written in 1 del 2u del t square minus del 2u del x square plus alpha del u del t plus beta del u del x plus gamma u equals to f x t, where t greater than 0, t represent the time variable, and the parameters alpha, beta, gamma, these are functions of x and t. In particular, they may be constants. Now, to explain the dispersion, we take the 0th order term from equation 1. So, now we are going to solve equation 2, where there is one extra term lambda into u in the one-dimensional wave equation. Now, we look for a solution which is called the uniform wave. So, for that we assume solution in the form u equals to phi kx minus omega t, where k and omega are real numbers, k is called the wave number and omega is the frequency. The function 3 is called the uniform wave because it represents a wave propagating with constant velocity c equals to omega by k. Now, if lambda equals to 0, we can prove the value of omega is plus minus k, and the solution becomes u is equal to x plus ct plus g into x minus ct. So, which is nothing but solution of wave equation. Now, if lambda not equals to 0, then if we substitute 3 in equation 2, it will give an equation omega square minus k square phi double dash plus lambda phi equals to 0, where phi double dash represent derivative of phi twice. Now, solution of this equation can be obtained easily, but if we want a bounded solution, then lambda by omega square minus k square should be a positive number. So, for that case, the solution can be written in simple form, which is given in equation number 4. So, phi, which is function of kx minus omega t, is equal to a into e to the power I kx minus omega t. Now, we are substituting 4 in equation 2 and we obtain a relation omega square minus k square equals to lambda, or omega k equals to plus minus square root k square minus lambda, and this relation is called dispersion relation. So, dispersion relation gives us omega as function of k, which is given in equation number 5. So, in case of non-dispersive wave, lambda equals to 0, and for that case omega k equals to plus minus k. So, for non-dispersive wave, we can say that omega is equal to some constant into k, whereas for dispersive wave, omega k is not a linear function of k. Thus, the frequency omega is a function of wave number k, and the velocity c is also function of k, and this is called the phase velocity. I have already defined phase velocity, and for in case of dispersive wave, you can see that c is not now a constant, this is function of k, or in other words we can say that dc dk is not equals to 0 for a dispersive wave. Since the uniform wave is dispersive when lambda not equals to 0 and non-dispersive when lambda equals to 0, the additional term or the 0th order term in the wave equation gives rise to the dispersive wave. So, we can conclude that in equation 2, the lambda into u term or the addition of 0th order term gives rise to a dispersive wave. Now, suppose there is a dispersive wave and the wave number of the different waves are k1, k2, kn. Now, the joint effect of these waves is represented in equation 6. So, ut is represented as linear combinations of all the waves having wave number k1, k2, kn, and this function satisfies 2. That means, we can prove that the 6 or u having expression which is written in 6 will satisfy the equation 2, provided omega j equals to omega j some function of kj and omega j equals to plus minus square root kj square plus lambda, where lambda is not equals to 0. If lambda is not equals to 0, the terms in 6 corresponding to different kj will propagate at different speed, and that will result a dispersion of the wave. So, in this way we can visualize what is dispersion of wave or the phenomena of dispersion of a wave train. We can generalize this taking continuous limit. Of course, the limit will exist as j tends to infinity. So, for that case we obtain the Fourier integrals u equals to integration minus infinity to plus infinity a k e to the power I k x minus omega k t dk. Here omega is not constant, this is function of k. and you can show that such solution is also dispersive for lambda not equals to 0. Now, it is to be noted that in case of dispersive wave, the solution obey the law of conservation of energy. To prove that, let us first define what is energy. Energy integral E is defined as half of integration minus infinity to plus infinity del u del x del u del t square plus del u del x square plus lambda u square dx. So, this denotes the total energy of the system. Del u del t, this corresponds to kinetic energy, del u del x corresponds to potential energy, and this is the total energy. Now, if you take the time derivative of u, that means if we differentiate 8 with respect to t, you can see the dE dt is equal to 0 for this equation if the u satisfies equation 2. That means for the dispersive wave, energy remains conserved. So, we can conclude that in general a dispersive wave is a solution of the form 3 this is 3 for which the frequency omega is a function of real valued function of the wave number k and has a non-constant velocity c is equal to omega by k. On the other hand, for a non-dispersive wave, this phase velocity is always constant. In this section, we shall discuss about the phenomena of dissipation. Dissipation is defined as a process where energy is transformed from one form to the other. The example of dissipation process is friction, heat transfer, etc. It is an irreversible process. Some scientists defined dissipation process as the conversion of mechanical energy to the heat energy. In case of wave motion, dissipation means decrease in amplitude. In this section, I shall discuss the dissipation process taking an example of wave equation. And in the wave equation, we shall relate the term which is responsible for dissipation. Now, we are going to the slide presentation. To explain the phenomena of dissipation, we take the homogeneous part of equation 1 which is written in equation 9. So, now we are interested to study equation 9 del 2u del t square minus del 2u del x square plus alpha del u del t plus beta del u del x plus gamma u equals to 0. And in this equation, we considered alpha, beta, gamma as constants. And we also have considered that alpha as a positive constant. And we shall show that the constant alpha corresponds to the dissipation. First, we take two characteristic direction x plus t and x minus t, and now we change the coordinates to characteristic direction xi equals to x plus t and eta equals to x minus t, and in terms of xi and eta, the equation 9 is transformed into del 2u del xi square minus alpha plus beta by 4 del u del xi plus alpha minus beta by 4 del u del eta minus gamma by 4 u equals to 0. Now, we give a transformation to the dependent variable. In this way, u equals to w into e to the power alpha plus beta by 4 into eta minus alpha minus beta by 4 into xi. With this transformation, equation 10 reduces to the equation del 2 w del xi del eta plus lambda by 4 w equals to 0, and we can solve equation 12 easily, where lambda is equal to alpha square minus beta square minus 4 gamma divided by 4. Now, if we come back to the original coordinate system x and t, our required solution is u is equal to w into e to the power beta by 2 into x minus alpha by 2 into t, where w satisfies the equation 12, or in other words we can say that the value of w can be obtained solving equation 12. Now, we shall show that u will satisfy the conservation energy law for alpha equals to 0, but if alpha greater than 0, then the energy will dissipate. So, first of all we assume that beta equals to 0, then energy integral can be written as E equals to half integration del u del t square plus del u del x square plus gamma u square dx. Now, if you take the time derivative of the energy, so here we have taken the derivative of u. So, right hand side is del u del t del 2u del t square plus del u del x del t u del x del t plus gamma u del u del t. Now, we take common the term del u del t from first and third term. So, that gives del u del t into del t u del t square plus gamma u plus del u del t into del t u del x del t. In the third line, we substituted the value of del t u del t square plus gamma u from the given equation. Then after some simplification, we obtain the last line where the value of d dt is equals to minus alpha integration del u del t whole square dx. The value of the integral del u del t whole square dx is a positive quantity, and we have assumed that alpha is a positive number. So, the equation says that d dt is less than 0, less than or equals to 0 for alpha greater than 0. That means the energy will decrease with time, or in other words energy will dissipate, and this dissipation, for this dissipation the term alpha is responsible. Therefore, in the equation, if we go back to the original equation or equation number 9, so in this equation the term alpha represents the dissipation of energy. At the beginning of this module, we have started with a linear one dimensional wave equation, and from that equation we discuss the phenomena of dispersion and dissipation. We also relate the terms which are responsible for dispersion and dissipation. Now, I am going to discuss the domain of dependence of the solution of general wave equation. We consider the Cauchy problem of non-homogeneous wave equation. So, the problem is given by del 2u del t square minus del 2u del x square equals to f x t. Since f is present, the equation is called non-homogeneous, and this is the Cauchy type problem. That means the values of u and its time derivative del u del t are prescribed at initial time, that means at time t equals to 0. Therefore, we are going to solve equation 14, and we have already derived the solution of this type of equation, and the solution is given by u at p. P is a fixed point in xt plane and which has coordinates x and t, is given by half of gq plus gr plus half of integration r q to r hx dx plus half of double integral fxt dx dt over the region D. If we see the figure, so this is our P. We want to find the value of u at the point P. So, its value depends on the value of g at q and r. That means value of g at the point q and at the point r, and we have to know the values of h along the interval q to r. So, h is prescribed along the interval q to r, and value of the integral f over the region D. Value of the integral f over the region D, where D is the region which is bounded by the lines PQ, QR and RP. So, the solution of the homogeneous wave equation depends on the values of some function within this domain, and this domain is called the domain of dependence. It is to be noted that the value of p at some particular point does not depend on the values of the function outside the domain D. So, in this solution, q is a point which is less than r, and where q and r are the points where the characteristic through p intersect the x axis, and D is the domain bounded by this characteristic and x axis. The closure Debye is the domain of dependence of inhomogeneous wave equation. Now, we are interested to find the domain of dependence of equation 9. So, this is our equation 9. So, if we compare this equation with the inhomogeneous wave equation, for that we need to take the term alpha del u del t plus beta del u del x plus gamma into u to the right hand side of this equation. So, if we compare equation 9 with the inhomogeneous equation, we can write in this form del 2u del t square minus del 2u del x square equals to some function capital F, which is function of x t u del u del x and del u del t. For equation 9, capital F is small f minus alpha del u del x minus beta del u del t minus gamma u. So, this is the expression for capital F for equation 1. So, the solution for this equation or equation 1 can be written as u at p equals to half gq plus gr. The solution is same to solution 15, only small f will be replaced by the function capital F. So, solution of 1 is given in equation number 18. But if you observe the solution u at the point P depends on the value of u also, which is in the double integral. Therefore, the solution for this case cannot be written in explicit form. However, if we think about the domain of dependence of u, we can see that u depends only on the behavior of the Cauchy data in the interval QR and the functions alpha, beta, gamma and f in the domain capital D. Thus, the domain of dependence of equation 1 coincides with the domain of dependence of equation 14. Therefore, in module 2 of chapter 10, we have discussed the phenomena of dispersion and dissipation taking a simple wave equation. We have also obtained the domain of dependence of that equation. Now we end this module.